So hi and hello. Welcome to our channel named Elko Exploration. My name is Samir and today we will be going to continue the remaining part of QuickSort. In the previous lecture I have shown you the working of partition algorithm and the logic behind the partition algorithm. Let me quickly explain how the partition algorithm works because we will be needing further. Now in the partition algorithm, the main objective is that the pivot should be at its correct position, in which the elements which are smaller than pivot should be on its left and elements which are greater than pivot should be on its right. Now here I have selected pivot as first element. Now this is the main condition. I will be pointing at 0 and j will be pointing at I plus 1. Now we will check whether a of j is less than equals to pivot, that is 7 is less than equals to pivot. No, it's not, so we will simply increment j. Now again we will check whether 1 is less than equals to pivot. Yes, it is, so we will increment the I and we will swap a of I with a of j and we will increment the j as well. Now again we will check whether 2 is less than equals to pivot. Yes, it is, so increment the I and swap a of I with a of j. And increment the j as well. Again check whether 5 is less than equals to pivot. No, it's not, so increment the j. Again 3 is less than equals to pivot. Yes, it is, so increment the I and swap a of I with a of j and increment the j as well. Again check 6 is less than equals to 4. No, it's not, so increment the j. Now actually j is out of bound, so at last we will swap pivot with a of I. So 4 will be here and 3 will be here. Now we can see that 4 got its correct position, in which the elements which are smaller will be residing on the left part of pivot and the elements which are greater than 4 will be residing on the right side. So in this way the partition algorithm works. Now let's go further. Here I have taken the same example. After applying partition algorithm, the array will look like this, in which only the first element got its correct position. Now after applying the partition algorithm on the whole array, the first element will go at its correct position. So why can't we apply the partition algorithm here also and here also, right? Due to this, let's say the element 3 will be act as a pivot, will get its correct position, and similarly the 5 will act as a pivot, will go to its correct position. Let me show you how. Let's take this example only. 3, 1, 2, 4, 5, 7 and 6. Now we will apply partition algorithm from index 0 to 2 because the element at index 3 is at its correct position, and from 4 to 6. Now after applying the partition algorithm in this part, 3 will act as a pivot and it will go at its correct position. So the array will look like this, right? 3 got its correct position, and again we will apply partition algorithm on this part because it is not at its correct position. So here 2 will be act as a pivot, right? And 1 is lesser than 2, so it should be on the left part. So 1 will come here and 2 will come here, in which 2 got its correct position, right? Again we will apply partition algorithm on this part. 1 will come here. Why? Because this contains only one element. This contains only one element, so we don't need to go further because it is already in a sorted manner. Now let's come here. Now 5 will act as a pivot, right? After that it will go at its correct position. Now we can see that element 7 and 6 are greater than 5 and it is on the right side only, so there is no need to do anything. Simply copy 5, 7 and 6. Now we can see that 5 got its correct position and we have to apply the partition on element 6 and 7. 7 and 6. Now applying partition algorithm on this 7 and 6, in which element 7 will act as a pivot and 7 should go on its correct position. Now we can see that 6 is lesser than 7, so it should be on its left side. So 6 will come here and 7 will come here, in which 7 got its correct position. Now again we will apply partition algorithm on element 6 and 6 will come here. Now here there is only single element, so we don't need to go further, and it is already in a sorted order. Now if we see that the element which I have highlighted in blue are actually in its correct position, 1, 2, 3, 4, 5, 6 and 7. So actually in this way we are sorting the whole array, dividing the array and applying partition at every level. This will be the pseudocode. Now I have named the function as QuickSort, passing the array A, start index and end index. Now we will check whether start is equals to end. If yes, then we will simply return A of start. Now we will call the partition algorithm, because after applying the partition algorithm, the first element will go at its correct position and we need that index because we don't have to worry about that particular element. And after that we will again call QuickSort, passing the array A, start index and mid minus 1, and again call the QuickSort, passing the array m+1 and end. Here after applying QuickSort on this array, 4 was already in its correct position. Only we have to call the QuickSort for this part and this part only. Right now, observe here in this pseudocode what actually we are doing. We are calling this QuickSort, let's say QS, on array A, and then we will be calling the partition algorithm and storing that answer in M, start and end. Now again we will call the QuickSort recursively, passing the array A, start index and m-1, right? Again calling the QuickSort, passing the array A, m+1 and end. Now if this function is taking t of n time, and we have seen the time complexity of partition algorithm, it will be order of n. What about this function? What will be the time complexity? Let's calculate. If an array A contains n element, then the time complexity is t of n. But what about this? We don't know the number of elements, so let's calculate it. Here to find the number of element, there is a formula n minus start plus 1. Similarly, m-1 minus s plus 1. This one and this one will get cancelled, so m minus s. Therefore t of m minus s. What about this? It will be e minus m plus 1 plus 1. If we calculate this, it will be e minus m. So this will be t of e minus m. Now let's find the recurrence relation. The recurrence relation will look like this. T of n is equals to order of 1 if n contains only single element, or else n plus t of m minus s plus t of e minus m. Now there will be two cases. Let's discuss that also. If the number of elements in an array are n, then the division will look like this: n by 2 and n by 2. This will be again n by 4 and again n by 4. Here also n by 4 and again n by 4, and this will go further. This will be n by 2 raised to k, and here also n by 2 raised to k, right? So what will be the value of this? It will be 1, because at last there will be only single element in an array. So if we calculate this, the value of k will be log n base 2. Now let's find the cost. For partition at this level, the cost is n. For partitioning this element, it will be n by 2, and for partitioning this also it will be n by 2. That will be n. Again, for partitioning it will be n by 4. Here also n by 4, n by 4, and n by 4. Therefore into 4 it will be n only. Now we can see that at every level the cost is same. So the time complexity will be cost at every level, that will be n, into number of levels, that will be log n base 2. This is n only. Right? Let's take one more situation. What if an array contains element 1, 2, 3, 4, 5? So the first element will be pivot, right? So after partitioning, the element 1 will be at its correct position, but we can see that it is already in its correct position. So we will call this part. And again 2 will be the pivot, and we can see that the elements which are greater than 2 are already on its right side. Same goes to 3, 4 and 5. So if an array contains n element, then at left there will be 0 element, but at right there will be n minus 1 element. Again here also at left it will be 0 element, and at right it will be n minus 2 element, and so on. So at last there will be 0 element and there will be only 1 element. Right? Now what about the cost? At this level the cost for partition will be n. At this level the cost for partition will be n minus 1. At this level the cost will be n minus 2, and so on. At this level it will be 1 only. Now let's calculate the cost. It will be sum of first and natural number. N. If we calculate this, it will be n into n plus 1 by 2. That will be order of n square only. So what we can conclude by seeing these two situations: if an elements are not sorted, then it will be order of n log n, and if it is sorted, the time complexity will be order of n square. So this will be our best case and this will be our worst case. What about the average case? Since we are actually dealing with sorting, so most of the time the elements will not be in a sorted manner, so the average case will be order of n log n only. In the start of the previous lecture, I have said you to remember the time complexity of a merge sort, right? So merge sort and quick sort, best case, average case and worst case. Now the best case for merge sort will be order of n log n. Here also the average case will be order of n log n, and for the worst case it will be order of n log n. But what about the quick sort? For the best case it will be order of n log n. For the average it will be n log n. But what about the quick sort? It will be order of n square. So we have to remember this part. If in an array the elements are in sorted manner and we are applying the quick sort, then we will get the worst case time complexity, that is order of n square. But which one is efficient? Actually this one. How? Because we are actually dividing the array meaningfully, but here we are actually dividing the array always n by 2, n by 2, n by 2 and so on. And in the merge sort we are dividing the array, conquer part is also there and combine part is also there. But what about the quick sort? There is a division, there is a conquer, but there is no combine. Now let's take this example only, 4. So after applying the partition algorithm for the first time, the resultant array will look like this. Now 4 got its correct position and we will divide it in this way. and actually we don't need to combine it because all the process are happening in that single array itself. So due to this, it is actually a partial divide and conquer application. So thank you.